Let's talk about the project. So the project is based on this idea that we have a wheel attached to a car. And that wheel is modeled as a free body diagram. Down here, you can see here's the vehicle. Here's my vehicle. Here is where my wheel is attached. I guess you could call it the axle. Probably not, but it's right above it. However, it was modeled. And we can see we've got these different components attached to it. So we have the spring here. We have the damper. The damper here. So here's my damper. Here's my spring. Spring and damper are also connected to this part down here. So these are my dots. And then we have gravity pulling it down. Gravity pulling the axle down, and then here we have the wheel as another spring that's modeled. So your tire is modeled as an elastic spring. Okay, so there's our free body diagram. So notice when we have F equals ma, we sum in the x and y direction. There's nothing in the x direction, so we just have summing in the y direction. So we have y direction here, y direction here. Okay, here's a list of all the variables that pertain to this model here. Note gravity is 9.81, so use that in your document. But if we do F equals ma in the y direction at our 2 points, we get this equation right here. So you should understand that based on physics. However, in order to model the damper, modeling the damper is the damper constant, so c times the velocity, which the velocity equals the position, the derivative of the position, or cx prime. Okay, so that's where these primes come into play. And note, acceleration is the second derivative of position, so that's where the acceleration comes in. So, but it's really F equals ma, based on that free body diagram. That's really what it comes down to. And note, this x here, so if for a spring it's kx, this x is based on the fact that this distance here and this distance here, they compress. So it depends on what x is for my spring. Okay, so in order to solve this, this is a second order differential equation, which is beyond our comprehension, beyond our understanding. So we're going to turn it into a first order differential equation, which is also beyond most of your guys' understanding, but that's okay, because we're going to turn it into a matrix problem. Okay, but what we do is we go ahead and instead of using x prime and x double prime, we're just going to add in velocity. So velocity equals x prime. So therefore, this here turns into x prime, and this turns into the velocity prime. So anyway, we have these additional variables that come into play. So now I have a bunch of equations that are first order. Once again, totally not important. What's important is this down here, where they simplify to this, which is just a matrix problem. So it's just matrix, solving systems of equations using matrices. Okay, so this here, this here, this here, and this here are pieced out into these matrices, F, G, X, X prime, K, and M. Note, this looks like a system of equations. This looks like a system of equations. Okay, so we rewrite this as F plus G plus KX equals MX prime. Okay, where X and X prime, these are our unknowns. In this part right here, and this part right here. Okay, so you're going to construct F, G, K, X, and M. Okay, but note, once you construct those, you go on ahead and do your first function. So you can write your first function vehicle data. Because vehicle data is just reading in all of these constants from a file, because it depends on what kind of car you have, because the mass of the cars are different, the springs are different, the dampers are different, the heights are different. All that depends on the vehicles. So you can read in that data, and then you can go ahead and construct F, G, M, and K. Okay, because you don't construct X and X prime. These are unknowns. We don't construct these. Remember, X equals something. X prime equals something. That's what we type in MATLAB. You know, so we don't say X equals anything in MATLAB. We don't say X equals XW, UW, etc. It's X equals the solution. Okay. So, but once you know that, then you can go ahead and do vehicle data. Okay. So, the data. The data is going to be read in from a file. This is what the file contains. This is what the file looks like. So it's just like in your homework where you read in data and assign it appropriately. So if you have a compact car, using this for MW, this for MV, this for your spring constant, this for your damper, this for your tire constant, this for A, and this for B. Okay, so you'll read matrix, you'll define the vehicle type, which is dependent on your input. You will construct F, G, K, and M based on how you wrote them in your on a piece of paper. And then that's it. Then you'll have these outputs. Okay, RO is also needed for one of your matrices. Okay, so that's our last constant that we need. That doesn't come from the file. Note, you need to have these pieces here. You need to have an H1 line and a descriptive text because you will be graded on your comments for your project because you have more time. Okay, so vehicle, we have 4 different kinds of vehicles we're going to look at: compact cars, mid-sized car, truck, or industrial and military. Note, there's two words for the last one, so make sure you use that. And there we go. We can write vehicle data. Okay, continuing. We're going to assume that our car hits a bump. So we're going to look at a single bump, so literally a single bump, and then followed by flat road, or we're going to look at a bumpy road, which is sinusoidal, which that's a terrible sine wave. A bumpy road that looks like that. Okay, these are the variables that correspond to these equations. So there's lots of variables, lots of equations, but that's what it comes down to. If there's a single bump, L is the length of the bump for the single bump. L here is the length of the period, I guess, of the sine wave, or the period of sine wave, or the length of a single bump. But that's what L is. V is velocity of vehicle, etc. Okay, so you'll see these equations later on. Okay. The hard part is the suspension system function. The suspension system function is to solve F plus G plus Km. Nope, not Km. Kx equals mx prime. Solving this differential equation. So this goes through how to solve it. Solving it is broken up into 3 pieces: finding the static solution, finding the homogeneous solution, and finding the particular solution. So this goes through the entire the documentation goes through how to solve it, but you'll notice some of these equations are in blue. The blue equations are the ones that are most important. So this is how we find XE. So note, K is a matrix, negative G is a vector, so it looks like AX equals B, right? So we solve that for KE. Check. That one's done. So then we have the dynamic solution. The dynamic solution is this Q here, where it's this piece here. It's homogeneous plus the particular. So the particular solution depends on the road type, where if we have a single bump road, then here it is. XP equals S1 plus S2T. And the reason for that, it's mentioned in the document, but that's what it comes down to. Here is how you find S1. Once again, it looks like AX equals B, so solve it accordingly. And here's how we get X2. Once again, wrong one. Once again, looks like AX equals B, where 0 is my B vector, so solve accordingly. Okay, and then put it together. For a bumpy road, this is our solution. K equals, which we don't need this T here. Technically, it's a function of time because it's a sinusoid, and we've got this T here. But technically, it's just K, or X of P. But here's what it looks like, where S is solved using this equation, where Q equals SF, where S, F, and Q are constructed with those matrices. So there's a little bit more to finding it with a bumpy road, but it's really just constructing the right matrices. And once again, it looks like AX equals B, so construct it. And here's S and Q. The last piece is the homogeneous solution, which is a little bit harder because we're not going to get to eigenvectors and eigenvalues until after the project is due. But this is our equation that we are using to solve for XH, this one right here. Okay, where R1, lambda 1, R2, lambda 2, these are solved for using this equation here. This here. When you type that into MATLAB, it's going to give you an X matrix where the columns of X are R1, R2, R3, and R4. It's called the eigenvectors. And then it's going to give you a diagonal matrix, the D matrix, where you have lambda 1, lambda 2, lambda 3, and lambda 4, which are the eigenvalues there. Okay, so you will take those values and use that to construct this matrix. The last thing you need is these constants. C1, C2, C3, and C4 are still unknown, but we solve for them using this equation down here. This equation down here, where xp of 0, note xp is a function of time, so 0 is just at time equals 0, or the first column. But anyway, once again, looks like ax equals b, solve for c. These c values get plugged in up here, and there you go. You have the whole thing. So once you have xp, once you have xh, and once you have xe, then you can solve for x, the complete solution, where x equals xe plus xh plus xp. Okay. And then x is your final vector. And note your x is going to be a 4 by n vector, n being the number of time values we have, where each of these is a big long vector that contains the solution for the position of the wheel, the velocity of the wheel, the position of the vehicle, and the velocity of the vehicle. Okay, which all those relate all the way back to these variables here. So that's where you get the suspension system, solving your solution. Okay, so takes in your road type, takes in your this piece right here, which pertains to a bumpy road. It takes in the matrices you constructed with your vehicle data and your time vector. Okay, you'll use all of that to solve for x. Okay, solve for the static solution, xe, solve the particular solution, xp for a road type given a bumpy road or a single bump, and then a homogeneous solution using what we just mentioned. Note, because of finite precision, the fact that we don't have infinity, you will get imaginary numbers, so just convert them to real values using the real function. Okay, and then solve for your full complete solution. Once again, have your descriptions. Vehicle simulation. Your vehicle simulation is putting it all together. So this is what you're going to essentially use in order to call in your script files, because vehicle simulation takes in all the parameters for the simulation. All the parameters for a given vehicle, for a given road type, for a given bump. This is for a given bump information, for how fast the vehicle is going, for how much time it's going to take, like how much time you want to follow the road after it hits the bump. Okay, so that's what all of those mean, where you're going to call your vehicle data function, call your suspension system function, and get a final result of x and t. Then you have your simulations. So you're going to write, you're going to call your functions for all your vehicle types. So all 4 vehicle types. So for your compact car, your mid-sized car, your truck, your industrial and military, for each of your bumps. So you'll call it 8 different times. Okay, and you'll use these parameters for your vehicle simulation function. And then given your results, you're going to go ahead and save your results in a file. You're going to add your results to the Excel file that you read in from vehicle data. And you're going to print things out and you're going to plot things. Okay, so create figure 1 and figure 2. So pretty standard. There's a lot to it just because you're doing a lot with the data that you generate. Okay, you're doing all the things for them with the data you generated. The last one is investigations. And this one is a little bit more trying to play around with whatever we're looking at. So you're going to investigate how long it takes a car to settle after a single bump. So you can imagine after a car hits the single bump, it's going to go ahead and bounce a little bit and then flatten out. And we're going to figure out how long it takes to flatten out. So bump and then settle. something like that for a single bump. Right? For a bumpy road, it will not settle, obviously. It will just keep going up and down, up and down. Okay, but you want to see how the suspension system reacts to that up and down, up and down. Hopefully it'll be a little bit more stable than the wheel. Okay, for the first one, investigate how long it takes to settle down after you hit a bump. Okay, so you're going to go ahead and look at different size bumps from 1 centimeter to 15 centimeters, which that's a big one. This is 6 inches, like you're hitting a pothole. With this, so one of the ways, so this describes one algorithm to do this. There's other ways you can determine how it settles, but this is one way to determine how it settles. So figure out, okay, go out to the number of times and check to see, okay, in the last, 10% of the data, look to see what your min and your max is, and if that difference is really small, then it's settled. Okay, that's essentially what you're going to do, or what you can't do. Come up with your own algorithm if you want, and then plot the number of road cycles needed to settle versus the single bump height to see how that changes with bump height. And then you're going to investigate the vehicle speed. So as you are going over a bumpy road, you'll notice it looks like this, and you'll see how your vehicle speed affects how much your vehicle is moving up and down. So you look at velocities from 5 kilometers per hour to 150 kilometers per hour, and you'll see, okay, what's the maximum displacement? What's the minimum displacement? Nope, not minimum. Maximum displacement, and you'll plot that over velocity. Okay. And then you'll put everything to report. So there is a programming project report template. So go ahead, fill that out, complete that, and then turn in all of your code.